Hi everyone, welcome to this video where I'm going to discuss about the error control concept of data link layer. So how we are going to implement error control, why is it important that we handle error control at data link layer, what are the different ways to implement error control. We shall discuss all of those things in this particular video. And also I shall give you some small examples for the three of the error detection techniques: VRC, LRC and two-dimensional parity check. So let's get going. First things first, do we really need error control? Why should we handle it? The problem is, in computer networks, there is no medium which is 100% error free. I cannot guarantee say that this medium does not induce any errors while transmission. When you are converting the data into signals and transmitting across the media, whether it might be a copper medium or optical fiber or even wireless medium, there is always some external factors which will influence your transmission. So transmission of signals across the media between two devices is always prone to external factors such as noise, your EMI, electromagnetic interference, and RFI, radio frequency interference, and atmospheric conditions. So this environmental interference and even physical defects in the communication medium can cause a random bit errors during data transmission. What do you mean by an error? So if I'm saying that there are many factors which might influence your transmission, errors might be induced. So what is an error? Error is nothing but if you're transmitting a bit as 0 because of any one of these reasons, if that 0 reaches your destination as 1, that means if it changes during transmission, that we call it as an error. Now just look at this diagram. Let's look at this example. Imagine that this is the data which is being sent from your sender. So at the sender side, this is your data, right? So from the sender, once it passes to the transmission medium, it is converted as signals for transmission. And because of some particular noise or some other factor, here one of the bit is changed to 0. The actual bit for transmission is 1, but at the receiver, it is received as 0. This is called as an error. Okay. And why should we bother about these errors? Just imagine a scenario where you're trying to transmit or you're trying to do a bank transaction where you want to transmit maybe 100 rupees to your friend, and for some purpose, because of a transmission error, an additional 0 is added. 100 becomes 1000. Do you accept it? You won't. Are you okay with it? You are not. So to maintain the accuracy and integrity of the communication, it's necessary to detect the errors and correct them if possible. You have to ensure that error control is handled at the data link layer, because physical layer's primary responsibility is to convert the data into signals and transmit them across the medium. It is up to the data link layer to ensure that the physical layer does not propagate errors, or the data which is being sent at the physical layer does not contain any errors. So error control is actually handled at your data link layer. Now, first, even before we talk about error control, let us also discuss about how many types of errors are there. Generally, errors introduced during transmission can be categorized into two different categories. The first one, they are classified into two categories. The first category is a single bit error. It means that within a data unit, if there is only one bit that is changed, then we call it as a single bit error. You can see that this is your transmitted data word, whereas at the receiver, you receive with one change in the data transmission. This is an error. There is only one error that has happened. This case is called as a single bit error. Okay. The second category is something what we call as a burst error. It means that there is always more than one bit that has been changed during transmission. It means there are 2 or more bits in data unit which are changed from 1 to 0 or even 0 to 1. In burst error, most of the people think that because of multiple errors, these errors always happen in continuous bit positions or only consecutive bits are changed, but that is not the case. So that is the reason. In case of burst error, it is not necessary that only consecutive bits are changed. The length of the burst error is measured from the first changed bit to the last changed bit. This occurs when the duration of noise is longer than a bit duration. That means when you are sending some data on the wire or some via a medium, there is some noise which has affected the medium. The amount of noise is more than 1 bit duration. That means the noise, if the noise affects multiple bits during transmission, then a burst error is going to happen. Let me show you something. So imagine that this is your transmitted data word and this is to be transmitted across a medium. And if the receiver has received like this, the reason why we call it as a burst error is, if you see, this is the noise, this is your noise, and this noise has impacted this particular data bits. And rather than, just as I told you, rather than assuming that the bit positions will be always in continuous positions, there are 1, 2, 3, 4 errors, but the length of the burst error is always calculated as 5, because you have to calculate the bit positions or the position of the bits from the position the first error has happened to the position where the last error has happened. So 1, 2, 3, 4, 5, 6. Actually, this is 6. So let me change it to 6. Okay, my mistake. So the length of the burst error is 6. You can see the length of the burst error is measured from the first changer bit to the last changer bit. So this occurs when the duration of the noise is longer than a bit duration. This is called as a burst error. So we have to deal with both single bit errors and also burst errors as well. Now let us talk about how error control can be implemented at your data link layer. There are basically two strategies of implementing error control. One of it is called as error detection. The other one is called as error correction. Yes, the name itself tells you what they usually do. So error detection techniques detect whether the received data contains any errors or not. Whereas error correction techniques can not only detect the error, but also can identify which bit positions have been received with errors so that we can correct them. Correction is very simple. If I know which bit position has been received as with an error, I can simply change it from 0 to 1 or 1 to 0. That's what. Now, let us talk about first error correction. Addition of enough redundant information along with the original block of data to enable the receiver to deduce what the transmitted character must have been. In other words, we add enough redundancy. Redundancy is the additional information that we add for the purpose of error control. So if you add enough redundancy so that the receiver is able to deduce which bit positions are received as errors, and it can generate the original data, then we call it as error correction techniques. Error correction techniques are also called as FEC codes, forward error correction codes. Whereas the case with error detection, inclusion of only enough redundancy to allow the receiver to deduce that error has occurred, but not where the error has occurred. So in such cases, because the receiver cannot reconstruct the original data, what it usually does is the receiver asks for a retransmission of the data. So both are different. Error correction actually adds enough redundancy information for the receiver to identify where the error has occurred, and also to generate the original data by itself. Whereas error detection techniques will only tell you that an error has happened. It does not tell you how many errors came or where the bit positions are. So in that case, the receiver usually asks the sender for retransmission of the data. So these are the two different ways of handling error control. So to implement error control, we usually consider a frame consisting of m data bits, and we add r redundant bits, which we also call them as check bits, or in some cases we also call them as parity bits. Okay, the total number of bits is now n is equal to m plus r. An n bit unit consisting of both data and check bits is referred to as an n bit code word. Now, if this is my original data, okay, this is my original data word, which might consist of m1, m2, m3, m4, 4 data bits. Now, in order to implement error control on this data word, what I usually do is I add some redundant bits. Let me assume that r1, r2. Okay, here m is equal to 4 data bits, r is equal to 2. So a combination of these two, which gives me the entire code word that is now being transmitted to your receiver. So your code word consists of your data word and your redundancy. So in together off, we get 6 bits, m1, m2, m3, m4, and r1, r2. The purpose of adding this redundancy, how many bits we should add, it is all dependent on the technique that we implement for either error detection or for error correction. This is called as a code word. Okay. The redundancy information is implemented for the receiver to verify for errors, or to verify the data has been received without any errors or not. Of course, the amount of information that we add here is dependent on the technique that we implement. Now let us talk about the error detection techniques. So error detection involves checking of the received data for any errors. Here please remember that how many errors, the number of errors or the type of errors does not have an impact here. So it doesn't matter if you are getting 1 bit as an error or 3 bits of as an error or it's a burst error. It will only tell you that an error has occurred. That's all. If errors are detected, the receiver requests for a retransmission, just as I told you, because the receiver does not have the capability of regenerating the data, then it will ask for the sender, or it will request the sender for retransmission of the subsequent data. There are 3 main techniques for error detection. I usually divide them into as parity check, cyclic redundancy check, also popularly called as CRC, and the third one is checksum. Okay, these are the 3 different error detection techniques. So in this video, I'm going to concentrate on parity check techniques, which are once again divided into 3 different techniques. So under parity check, we have the vertical redundancy check, VRC. The second category is longitudinal redundancy check, LRC. And the third one is 2-dimensional parity check, or 2D check, we call it as. So these are the 3 popular error detection techniques: parity check, cyclic redundancy check, and checksum. So let me start with first, which is your VRC technique. So a simple and least expensive mechanism for error detection is the simple parity check, also called as 1D parity check. So VRC is also called as simple parity check. Let me tell you, if you can count the number of ones and if you can tell whether the number is even or odd, that's it. That is just sufficient for performing the VRC. Here, in this case, what we usually do is we add 1 redundant bit, also called as a parity bit, is appended to every data unit such that the total number of ones in the unit, including the parity bit, becomes even. In simple terms, it doesn't matter what is the length of your data unit, you take it and you only add 1 extra bit or 1 parity bit, and the bit which you add will be either 0 or 1. If the number of ones in your data unit is even, then you put a 0 there. If the number of ones in your data unit is odd, add the parity bit as 1. That's all. Now, why you are doing this? Because ultimately what you have to look after is the total number of ones in your code word which you send to the receiver is always even. Now let me show you. This is your original data. You have to calculate the parity bit. That means you have to decide if your original data has got odd number of ones, your parity bit will be 1. If it has even number of ones, your parity bit will be 0. So based on that, you append that bit. So your data and parity bit are both appended and now transmitted to your receiver. So the transmission happens. Your receiver will be receiving the same data which you sent. So data plus parity bit. Your receiver, what it will do is it will do a simple parity check. It will once again count the number of ones. If the transmission does not have any errors, if there are no issues, you will get, if you get an even number of ones, then you accept the data to contain no errors and you pass it off to the upper layers. But if the number of ones is odd, then you know that there is some issue during transmission and you reject the data and the sender will retransmit to your entire data unit. Okay. Now, to just give you an even more better idea, you can see this. Consider this is your data word. Now count the number of ones: 1, 2, 3. 3 is odd. So your parity bit will be 1. Now why am I adding 1? Because in the code word, the number of ones should always be even. Okay. So once again, 1, 0, 0, 0, 0. Here the parity bit is 0 because there are no ones at all. And your code word will also be zeros. You take this data word 1, 0, 0, 1, 1, 0, 0, 1, 1. If you count 1, 2, 3, 4, 5, there are 5 ones here, which is odd. So what do? I add another one so that my code word will now contain an even number of ones, which is 6. Here, I have only one here, which is odd. So I add another one here now, which makes it even to 2. So this is usually we call it as even parity. In some cases, we can also come across the word called as odd parity, where we try to add the parity bit such that the number of ones in your code word is always odd. But generally speaking, most of the cases we only use even parity. VRC can detect all single bit errors that happen in each code word. Whichever code word you are sending, if there is a single bit error, it is easily detected. But the problem with this method is it can detect only odd number of errors. Now, if you take this for example, now let me take this, okay? 0, 0, 0, 0, 0. This is the code word which I actually sent to the receiver. But unfortunately, because of an issue, 0, 1, 1, 0, 0. This is the data that has been received at the receiver. Now the receiver, what it will do? It will simply count the number of ones. Now it will count the number of ones and it will get an even number because there are 2 ones here. Now the receiver does not have the capability of detecting this error and will simply assume that this data does not contain an error, and it will pass it on to your network layer, which should not happen. So your method, unless until there are only odd number of errors, it won't detect. It will not detect an even number of errors. So this is the problem with your vertical redundancy check or VRC method. Though it is the simplest method, it still has a drawback of detecting only odd number of errors in your code word. Now we will let us move on to the next one, which we call it as LRC, Longitudinal Redundancy Check. In this case, what we do is whichever data you want to transmit, you first arrange it into a form of a table or just like a matrix. And rather than adding just one bit, what you usually do is you compute the parity bit according to your column wise. So let me show you that. A parity bit is computed for each column, and this full block of redundant bits is now appended to the original data and sent to the receiver. Now what is it? Let's just assume that this is your data which is to be sent to your receiver. Okay. Now for this, if you want to calculate the LRC method, this is how you write it. You just arrange it in the form of rows and columns. And now for each column, you calculate the parity bit. So 1, 2, 3, 4. There is an odd number of even number of ones. So I added a 0 here. There is only one here. So I added another one. This is your parity bits. Rather than adding one parity bit for each block, now what I'm doing is I'm arranging the blocks in such a way in the form of a table and calculating the parity bits column wise. So for each column, I calculate the parity bit. Now if you see here 1, 2, 3, there are 3 ones. So I added another one so that in this column, my parity is always even. Once again, here there are 2 ones. So I added 0 here. There are 3 ones. I added a 1 here. There are 2 ones. I added a 0 here. There are 3 ones here, which is odd. So I added another 1 here. In this way, I added the entire block. And now the data which I will be transmitting is I will add this parity block, or I append the parity block in along with the original data. This is my original data. So once this is my data block 1, 2, 3, 4. Along with the 4 data blocks, now I am adding the calculated parity block also. Okay. Now the advantage of using LRC over VRC is that it can check all the burst errors. So if there are burst errors, this particular LRC method is more efficient than VRC because it can check for them also. An LRC of n bits can detect a burst error of n bits. So the number of bits that you add here, n is nothing but the number of bits that we are adding as parity. So these bits, so this code can actually detect a burst error of length up to 8. So if there are a burst length of 8 bits, this code can detect that particular error. Okay, it cannot detect errors where there are even number of damaged bits that are located in the same column position of different rows. That means in these particular rows, if commonly the same positions are changed, in that are even number of damaged bits that are located in the same column positions, then LRC will not be able to detect an error. This is the issue with LRC. In order to increase the efficiency of both these schemes, both VRC and LRC, we go for the third method of error detection, something called as two-dimensional parity check or 2D parity check. So the two-dimensional parity check can be used to improve the performance of the simple parity schemes. Okay. Now why do you do that? Simple parity schemes. So what we do here, sir? It's pretty simple. You add both. What do you mean by add both, sir? Once again, in this technique, put all the data bits are organized in the form of a matrix table, and the parity bits are calculated for both row and also column. In your VRC, we only calculated for row parity, or just we added one parity bit for each data block. Whereas in LRC, we arranged them into columns and I calculated the parity bit for each column. Here, what I do is, once again, I arrange them in the form of a table, rows and columns, and I calculate the parity bits for each row and for each column as well. And I append all of these bits together and then send it to the receiver. So all the calculated parity bits are then sent along with the data which are compared at the receiver side. As an example, let us once again assume that this is the original data that you want to send. Now for this data, if you want to implement a two-dimensional parity check, what you are going to do is you are going to arrange this data in the form of rows and columns. Okay, so this is what 1 0 1 1 0 0 1 1, and you have arranged this data in the form of these rows, and this is the row parity that you calculate, just like in your VRC method. So 1 2 3 4 5, there are 5 ones, which is odd number, so I added another one more as a parity bit. So these are the row parities that I calculated, and along with the row parities, I am also calculating the column parities, just like how you did in LRC method. So VRC method and LRC method both combined will give you a two-dimensional parity check. So instead of sending this data to the receiver, now what I will be doing is I will be transmitting this data, where I am going to add the parity bits for each computed for each row along with the parity block which has been computed for each column. So this is called as a 2D parity check. So what is the advantage? 2D parity is better when you compare with LRC and VRC, simply because it has the capability of detecting and correcting single bit errors, detecting 2-bit errors or 3-bit errors, and also it has the increased likelihood of detecting the burst errors also. A burst error of more than n bits is also detected by the 2D parity check with a high probability method. But there is once again an issue where if 2 bits in one data unit are damaged and 2 bits in the exactly same position in another data unit are also damaged, then the 2D parity check will not detect an error. And also an additional problem is the number of the amount of redundancy that we are adding for the two-dimensional parity check is quite big when you compare with the other schemes. So these are all the old schemes that we used to use, whereas now we are currently using a much more efficient and faster technique called as cyclic redundancy check for error detection. And also we have the third method which we use at the higher layers like your transport layer and network layer, called as checksum. So before closing it down, let me just show you some practical examples of these three methods. Now, suppose the following data blocks are received where 2D parity is used. Check if it has any errors. In order to do so, what we need to do is first we have to write them in the form of a table. So let me write it down in the form of a table. Okay. So 1 0 1 0 1 0 0 1. What I usually find in such questions is most of the students will not write the question properly. By when you're trying to copy it from the question paper onto your answer sheet, most of the people do take the binary data wrong. They will misplace 1 0 with 1 bit, or sometimes they will not write at all one particular data block. So please be careful and don't do such silly errors. So 0 0 0 1 1 0 0 1 1 1 0 1 1 1 0 1 1 1 1 0 0 1 1 1. And once again the last data block is 1 0 1 0 1 0 1 0. Okay, so this is how your 2D check is being made. Now let me just find out if it is given if the received code word are containing any errors or not. How do I do that? I simply calculate the parity bit. So 1 2 3. So this is correct because the total number of ones is always even. 1 2 3. There is a mistake here. 1 2 3 4 5 6. This is also okay. 1 2 3 4 5 6. This is also okay. I have to verify the column parities also. 1 2 3 4. This is okay. 1 2. This is okay. 1 2 3. This is a mistake. 1 2. This is okay. 1, 2, 3, 4. This is also okay. 1, 2. This is okay. 1, 1. This is okay. So now, as I told you, the two-dimensional parity has the capability of correcting single bit errors also. There are two parity bits which I found to be of error, and these two bits converge here. So I can identify that this bit position has an error. So how do I correct it? Simply put a rather than a 0, the original data must have been 1. So this is how a two-dimensional parity bit or two-dimensional parity check can be used to detect and correct single bit errors. Okay, now for this answer, it has errors. And because it is a single bit error, I can easily identify the bit position also. This is one example where we can implement 2D parity check. Whereas the next example is the serial port on a computer is set to transmit a file using 8 data bits followed by 1 parity bit. The port is set for even parity. The other computer receives the following 9-bit strings. Determine which are valid and which are not. So once again, though the question is huge, you have to understand that you are simply implementing even parity method. Now, for this purpose, if you want to determine whether the received code word is valid or not, count the number of ones in that. 1, 2, 3, 4. If the number of ones is even, you accept it as valid. So this is valid. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is odd number. So this is invalid. 1, 2, 3, 4. This is also valid. So this is also another example. How do you implement even parity? How do you check for errors using even parity method? The third example is find the LRC for the sending data blocks. So I'm given 4 data blocks and determine the data that is transmitted. So let me write it down here itself, which will be easy for us. Okay. So I have to find out in LRC, you usually find out the column parities and add that parity block towards the end, or append that parity block along with your original data blocks. 1, 2, 3, 4. It is a 0 here. 1. There is only 1, so I am adding another 1. 1 and 2. So 0 here. 1, 2, 3. 1 here. 1, 2 is 0 here. 1, 2, 3. It's an odd, so I'm adding another 1 here. 1, 2, 0 here. 1, 2, 3. So 1 here. So this is your LRC. You append this along with the data blocks and send it to the receiver. Okay. So you append this, append the LRC with your data blocks. This is how you implement the VRC, LRC, and your 2D parity check. So hopefully you understood these 3 error detection schemes. And in the next video, we will talk about the most efficient way of handling error control and implementing error detection, which is your cyclic redundancy check. So till then, take care. Thank you very much for watching. So do share and subscribe. Thank you.